Everybody in the back. We're starting now. So, thank everybody for coming. I know you came here expecting a Meetup and continuity and hopefully Meetup and cast. And we pulled a little tips to do today. So the timing kind of worked out. It was very serendipitous that our relaunch came right around the same time that we were had the opportunity to host the HBase Meetup. I think we're actually going to launch 2 days before this, and then once we got the date, we're like, fuck it, we're going to launch on the same day. So here we are. Anyone that didn't hear that this morning, we put out a bunch of releases, and basically stuff we've been working on for the past 4 years, we open source this morning. Probably all this type has applicability to the HBase ecosystem. And so the first 3 talks you're going to see are going to be around these 3 different projects that we released today. CDAP, which used to be called Reactor, and that's really our flagship product. Tygon and Cooper, and I'll leave it to these guys to go more into it. So it's a very exciting day, and I really thank you guys for coming here. And we'll get through a few past talks, and then we'll also have some talks from other individuals. So this is the agenda. I'm going to do a very brief project announcement, just to talk about what we did today, and all the new projects that we have. High-level overview of what they are, and a very brief few words about what the plan is for us as a company. Next, I'm going to introduce CDAP. CDAP is the Cast Data Application Platform, and that is our flagship product, and we'll talk more about that. Albert from the Cast team is going to talk about Project Cooper. Gokul from our Cast team is going to talk about Tygon. We have someone from Flipboard who will be talking about the insurance work they're doing there with HBase. And somebody from Disco will be talking about master technologies post HBase 1.0. Cool. So, without further ado, today we released a whole bunch of stuff under 100% Apache 2.0 license. And we renamed the code. So this will be the only slide that presents anything about the company and not the code that we deployed and released today. So don't worry, this isn't going to be a vendor. But I just want to provide some context. So we're Cast now, no longer continuity. We don't see this as a pivot at all. This is for the same mission, single access to powerful technology. Always been the mission of this company. We've always been building a developer-oriented platform on top of the Hadoop and HBase ecosystem of technologies. None of that has changed at all. The main difference is that we're open source now. So we've basically been building our platform, building these different technologies, working very closely with our first handful of customers to try to bring what we thought we were trying to build here. And that is, people in this room probably have more appreciation than anybody else of just how hard all this shit is. HBase is extremely powerful, but it's extremely difficult. And honestly, that's where the mission comes from. It is HBase and technologies like it. I don't think anybody in here doubts the power, the opportunity, the disruption, and all the potential of this technology. It's just really hard to use. And when you talk about major enterprise companies who have all of these big data problems, very difficult to use. And that's our mission as a company, is how do we bring access to a much broader audience of developers and organizations on top of that. So we are committed to essentially releasing 100% of the lines of code we have written in the past 3 years. Will be released by the end of the year. The vast majority has already been released today. And we are committed to building communities. We do not plan to maintain control over these projects over the long term. We don't know whether they're going to go to ASF, whether we're going to maintain them independently, or how that's going to work. We will work with our community as it progresses to turn the best out. But we are absolutely 100% committed to these being community-driven projects in the long term. That is our goal. That's what we're driving. That's who we are as a company, and that's what we're planning to do. Cool. So, what are the 3 things that came out today? So, some of you may have been familiar with Continuity React, what we used to describe as an application server for Hadoop and HBase. And now we have the Cast Data Application Platform. It's actually the same technology with a different way of explaining, describing, and essentially, yeah, it's really how do you describe the concepts of CDAP in a way that makes sense. And those concepts are now virtualization. And I'll dive more into the concepts of CDAP and why we call it virtualization, what that means. And then we'll have other members from the team talk about Tygon, which is a new stream processing framework for Hadoop interface, and Cooper, which is a cluster provisioning system that we built internally and we use extensively ourselves that we've also released to open source. We also have all these different open source project sites that we launched. So what we released today was CDAP.io, Cooper.io, Tygon.io, and Tempera.io. So those are non-commercial, fully open source project type sites that we plan to release control of and grow an external community around. We have tons and tons of technical documentation about all of our products and everything that we do, and all of that is now available online as well for free. CDAP came out as 2.5 today. Cooper came out as 0.98. Tygon came out as 0.1, which is kind of an interesting story, but Tygon is made up of 3-year-old technology from Continuity and 12-year-old, 15-year-old technology from AT&T. So it's made up of very mature technology, but it's a new incarnation of it, and we'll talk more about that. And then the icing on top of our day today has been hosting this meetup, and I really appreciate you guys coming and hearing what we have to say. So that was the intro, and now I'm going to give maybe 5 minutes or so on what CDAP is and why it's cool. So I mentioned that CDAP is a virtualization platform. So we describe CDAP as virtualization for Hadoop data and applications. So we're not talking about virtualization like virtual machines and running Hadoop on that virtual machine. We're talking the next layer up. So if you look at other virtualization styles, so you have Java, right? Java is virtualization, Java virtual machine. There's tremendous benefits from the JVM, right? We get code portability, higher level APIs, a lot of reusability, a lot of really nice functions that J2EE comes with that you don't have to re-implement. I don't build threading when I build a Java app, I use an executor service, right? So that application, that runtime gives you tremendous capabilities in the virtualization container. VMware and Docker and OpenStack technologies like that deliver tremendous value to many, many organizations, developers, ease of use, simplicity, efficient resource utilization, all the different kind of benefits around virtualization from a VM perspective. And then more recently, there's been a lot of stuff around SDNs, network function virtualization, and all the value and disruption that can bring to an entire existing ecosystem. So virtualization as a concept, I think is really, really powerful. It's very, very well known, and it's provided tremendous value in a lot of different technical domains in the past. And what we say is that really, really to enable the wave of adoption, the wave of applications and developers to actually build stuff on top of things like Hadoop and HBase, we really need this virtualization. We need a higher level with which to build, deploy, and manage our applications and our data. And that's basically the premise of CDAP, is bringing application virtualization and data virtualization on top of the Hadoop ecosystem of technologies. And so the way we would describe it is that Hadoop and that related ecosystem is really an operating system, right? Hadoop, a distribution like CDH or HTTP, these are really like distributed operating systems now in your data center. And we see ourselves as a distributed virtualization layer on top for developers and operations to actually build, deploy, and manage apps at scale. So this is a very high-level architecture diagram built on top of Hadoop. And what you see here is the CDAP layer. So what CDAP does is it defines a set of SPIs, service provider interfaces. So for all the different capabilities that you need for your applications and your data, whether that's how do I implement a file, how do I implement logging and metrics, how do I implement service discovery, all those different types of services that you need in your applications are defined as SPIs. Then we have our data and virtualization layers, and I'll go into those individually. And on top, you have a set of APIs, which are not just CDAP APIs. APIs are all different kinds of APIs. We have Tygon, which we'll talk about later, which is one of our APIs. We also have others that we support, like MapReduce, cascading. So we have experimental support for Spark right now. So the idea is to bring together all these different technologies, not to replace them. So what is app virtualization? We need to think about virtualization really as a way to create standardized containers that all your programs run inside. So if you think about the kind of myriad different projects that are available today to do processing on Hadoop, you have MapReduce and Hive and Tez and you have Spark and you have Storm and there are many, many more, and there are many that are left out. One of the issues to a developer, especially to enterprises and organizations, is each of those things were built by different teams at different times in different places for different reasons. And so the way that I might package and deploy and test my Spark job may be fundamentally different from how a Storm topology works. Maybe very different from how MapReduce works. And so as a developer, I have to actually learn each individual system to understand how do I get data in, how do I make my data available, how do I process it, how do I get the results. And if I want to put it into production, how do I collect the logs and metrics from it? How do I deploy it and package it? How do I upgrade it? Each of these systems has their own world on how all of this stuff works. The notion of application virtualization is to create a standardized container type that then integrates with each of these systems. And so what CDAP does is it says, look, you want logging and metrics and service discovery, you want some metadata, you want to do lifecycle management, you need to package your applications and deploy them and scale them. Those are all things you're going to do with every program type no matter what. You don't want to implement 5 different things for 5 different runtimes. And so you implement it once, and then you get to inherit all the other runtimes. So once you integrate your logging system, your metric system, your alerting system, your deployment and packaging system with CDAP, you get to use all of the different runtimes with it. Because each runtime is implemented as the standardized container. So that's at a high level kind of what the standardized containers are about. What it gives you is things like framework level guarantees. So we released recently as open source, and I think we talked about it in HBase Meetup, something called Tephra. Tephra is a transaction engine for HBase. That transaction engine really is one of the bridges between data virtualization and application virtualization, because what it does is it shields your application from failures. It shields your application from retries. It shields your applications from all the shit that happens in the distributed system, right? Which we're all very, very familiar with in this room. Distributed systems are very, very hard. If your application logic deals with failure mode of the distributed system, it's not really an application anymore, and you're just littering a whole bunch of logic around how to deal with the system. So framework level correctness, framework level guarantees are a really important attribute of what app container will be given, because it frees the application developer to just worry about that logic, and not the fact that if I implement a counter here in HBase, and then I implement a counter here in HBase, I can fail in the middle. Or if I update this column and then I write to another index table because I want a secondary index, but I can fail in the middle, right? These are very, very simple use cases for HBase are quite difficult to reason about without transactions. And that's why transactions are really important. So I talked a little about the development lifecycle, about cluster deployment, about operations, things like that. One of the things that's really cool about CDAP is the benefit of an SPI library. So everything that sits up here is actually has a hard boundary on top of an SPI. So for anyone who's familiar with dependency injection, which you're a Hadoop developer, you might not be, but many other developers use it extensively, and we use that a lot in CDAP. And so there are today 3 different full implementations of CDAP. There's the Hadoop Yarn HBase distributed version. There is a version called standalone. This runs on 1 JVM. It uses level DB instead of HBase, which is very, very similar. It uses your local file system instead of HDFS. And it just creates a really easy, lightweight way to run the entire platform on your desktop. And all of the runtimes work there. So you can run your Spark jobs on there, you can run your Hive queries on there, you can run MapReduce on there. You don't even have to worry about installing Spark, it's just there. And then the last mode is there's an in-memory mode. And the in-memory mode is really powerful because it's actually fully in-memory. It starts very quickly, and it's part of our unit testing framework. And so part of having standardized containers is how do I test Spark, how do I test MapReduce, how do I test cascading? Each of them will have their own ways. We have one unit testing framework that allows you to try out all program types in the same API. And so it's much, much simpler how you actually test in things like CI and development systems. So the goal is just enable developers to build applications, not to system build. Right? So much of what we do in this space is build infrastructure, services, and systems around the infrastructure just to enable it. And Meetup is really about putting folks back in. Data virtualization is really about having a logical representation of the underlying data. So we call these CDAP data sets. And data sets are essentially a programming abstraction that allows you to expose data as a specific pattern in many different ways. So this actually is not a super technical audience slide, but I would like to be a little bit more technical because of the nature of the audience. But as an example, what a data set allows you to do is define a certain type. So a good type in the HBase crowd is the time series data. Time series is very, very popular with HBase, very well suited for storing and querying time series. But time series requires schema design. Right? You need to understand how do I efficiently write and read all the different things from HBase. What a time series data set does, a time series data set is something that ships with CDAP. It's an implementation of time series on top of HBase. It exposes a set of RPCs, right? Time series data point, read from this range to this range, typical time series API. So you expose the domain specific API. That's how I would read and write like this HBase table, but in my API. But what data virtualization allows you to do is say, I don't want to expose this just as an RPC. I want to expose this data set as batch loads, like read and write maps. Or I want to run SQL queries on top of it. Or I want to write Spark code. And the ability to do that actually requires you to write a lot of glue and logic and understand each of those systems again. Sparks have RDBs. How do I get my HBase table into that RDB? Hive requires you to create tables. I have to create a table, right, a logical table, that points to an HDFS file or an HBase table and somehow inherits that schema. The way that a time series data set works is it implements all those things as code. So it exposes a schema. It exposes map readable, batch readable types of APIs that make them that one data set exposed in all those different ways without actually changing any code, without actually writing any code, and it gets the exact same data. So one of the other core concepts around this, around CDAP is that many applications on HBase today are really about real-time and batch. It's not just batch, it's not just real-time, it's about doing both of these things together. And that's one of the major tenets of data virtualization is we put data into the human into HBase. It shouldn't be like this sink where you go and I have to understand everything about it before I put it in. And then once it's in, I can only ask the question I said I was going to ask up front. Sometimes I want to write a Hive query and just run SQL commands. Now you have to understand the Hive. I have to download and install hcatalog. I have to do all these different steps just because I want to run a SQL query and find HBase data. Data virtualization contains the plugin. As soon as you use a time series data set, the schema is available and it can auto-import itself to hcatalog for you. You don't have to do that. So we have different sets of these different types, like geospatial indexes, time series, key value, holdout queues, things like that. And this is somewhere where, honestly, our hope is that as CDAP turns into more of an open source community project, that a lot of people from the HBase community can come and help build some data sets. It's very easy to use these data sets to abstract your application from HBase's API. Right? Why do I want Firebase? It gets inputs inside of my application model. And what I'm trying to do is read and write a geospatial index or read and write time series data. And so data sets are a way to give you that abstraction. And then expose it through these different mechanisms. Right? One thing I didn't mention is it also makes exposing it as an RPC, so for REST APIs, things like that very good. So, cool. Yes.
So the question is, we have an application right. So we have an abstraction there, we talk about containers, right? And then you're saying that you have APIs basically to let you monitor those, utilize those containers, right? And there could be Hive storage type, HBase, so you have to Spark, there will be various these things, and you have one interface through your API where you can push those data sets, right? So the question is, since you already defined the interfaces, right? And it's a virtualization layer on top of your cluster. That's how I'm trying to follow you. Yeah. So first of all, let's say I have a use case which I really don't know that if it's a HBase is going to be a qualifier for that kind of product, or it could be a high solution, and my developers have challenges adapting these new technologies. Yeah. And at the infrastructure level, you also want to see which is the most cost-effective solution, right? So, can we distribute the same prototype into several of these containers and observe some kind of performance?
Yeah.
Is that how?
Yeah. So I think the question is about essentially, oftentimes the way that you want to adopt this and try this out is you want to put a bunch of data into HDFS or into HBase, and then you want to experiment with the different processing paradigms, the different tools out there, and things like that, and do a bake-off basically, and compare and contrast. Is that right?
Yeah, basically, there is a way for us at once we can deploy these. We can use multiple containers at one time, and then still be able to function. Right?
Yeah. So
that's
so all of these containers, all of the application containers, which is where these different programming paradigms are running, those are Yarn containers, right? And so actually, this entire platform is built on top of, and you have a really good architecture diagram without tagging, but there's two. The way we kind of see our stack is that it's Yarn and it's HDFS. On top of Yarn, we have Twill. Twill is an Apache incubator project that we released that makes it really easy to build Yarn applications. So every Spark job you run, every logging aggregation service, every REST proxy, all those different services run inside of Twill, inside of Yarn. And so that's kind of one major component of it. And so ultimately, your ability to deploy many different things concurrently is about Yarn deploying those many different things concurrently. And what the virtualization layer does is allows you to connect all those things together without writing the logic to go from HBase to Hive, from HDFS to cascading. And in the future, and this is really the opportunity of CDAP, and a lot of the reason why we're open sourcing this is and the reason we didn't open source it yet is we kind of wanted some maturity on the SPIs. Right? The SPIs define what is a data application platform, what are the requirements, what does it need. And so the future is we can support other data stores, we can support a lot of other things without actually changing the implementation of your application. So the ability to try out different runtimes without having to actually understand the details of each of them is absolutely part of what we're trying to do. That answers the question.
Yeah, that really answers the question. And another thing that I'm trying to understand is service provider interface.
Yeah.
Right? I think there exists already SPIs kind of model today, which kind of gives you a leverage to use HBase like Phoenix. Have you heard of Phoenix?
Yeah.
Is that the same space? Does it fall into the same role?
So Phoenix is an API,
Yeah.
right? Not an SPI. So Phoenix is a SQL interface to HBase. It's a client API SQL interface to HBase. We would put it on the API side. And we actually are big advocates of Phoenix, and we're working with the Phoenix team on integrating with Tephra and things like that, our transaction engine.
We do use Phoenix in our implementation because of that curve that we have, but we have issues also because sometimes you can pass on some arguments which are invalid and HBase won't even catch it, and Phoenix passes it. So I'm kind of interested in how that works.
Yes. So I mean, so Phoenix is not integrated in the platform today, but I can kind of describe how it would be. So today, when you implement a data set in Java code, I don't remember exactly. Let me see. They don't have to build that much anymore, but there's an interface which allows you to expose schema in a system agnostic way, meaning it's not what's my Hive schema. It's just what's my schema, right? The schema is a generic thing about the columns and the types and all those types of things, right? And so the notion of how we would support Phoenix is to say that You don't actually have to write any more code. What we do is we create a bridge from that schema API that you exposed to the representation keys. Right? And that's the opportunity of CDAP, and that's exactly why CDAP needs to be open source. Our goal is not to squeeze money out of every user of CDAP. Our goal is to get ubiquity with CDAP, and to solve a lot of problems, to add a lot of value to the system. And I think that example is exactly the kind of reason why this layer is necessary. Virtualization doesn't have to be about performance degradation. When you run your Spark job, and that Spark job reads files from HDFS, even when it runs in the virtualized app container against a virtualized data set, that only has to do with how it starts and how it runs. Once Spark is talking HDFS, it's like there's no performance penalty. The benefit is in how you actually start it, how you actually manage it, how you run it, and monitor it. And that's why we feel that this layer is really an important step for Hadoop and for HBase, and just how to make it life a lot easier for everyone. Cool. So we have a lot more. Was there another question? Yeah. Yeah.
So it's possible to run Hadoop over a data set that is stored in massive core, massive data set that is stored in CDAP. So how do I get Hadoop and how do I store this massive core, how do I have database, and system? How does it happen?
Good question. So you're probably stretching the extent to which I understand how it all works now, but so there's two different things. So one is when you're in the standalone mode, you're in memory mode, versus when you're in the distributed mode. So those are three different. Sorry. The question is essentially, so we said that once you put your data into a data set, you can run a Hive query on it, right? But running a Hive query on a data set actually means writing something in the HCatalog, right? It means executing something against that. HCatalog requires the Metastore, which is like a MySQL database and all that infrastructure. So in distributed mode, we need to have Hive running. And we will talk about Cooper. Cooper is our cluster provisioner, and that's how we deal with all this stuff. But I believe that, and someone correct me if I'm wrong in the past, basically part of the configuration is where it's Hive. Right? So if you want to use Hive, that's Hive. Cooper makes it super easy to start it and configure it, so you don't have to worry about it. But I believe from a distributed mode, everyone's going to be taken offline. Essentially, I believe that in distributed mode, you have to have Hive running. And the question is, you don't actually have to talk to it. In terms of, I don't have to create a table. Because when Hive's there and I create the data set, it does it for you. So it does that kind of stuff. Right? So let's say I have Hive running, let's say I have an HBase table. To represent the HBase table in Hive, I have to run statements in Hive. Right? To create that table, to map the schema to it, I use the HBase storage handler, right? I have to understand all those ins and outs. And what we have is like a data set handler. There's a data set storage handler for Hive. And it will basically perform that for you and create the table for you per whatever schema is defined in that data set.
So you can pretty much transform a schema. Transform.
Yeah, well, it's ultimately that's Hive that does that, right? It's what the data virtualization layer does is says, look, you implemented this thing which says here are your columns and here are the types of those columns. And what CDAP will do is say, how do you bridge that into HCatalog? So what's the statement? What's the storage handler? So it becomes similar where in Hive there's a data set storage handler. In Spark there's an RDB for data sets. Right? There's data input formats and data output formats for MapReduce. For all these different systems, we create the plugins for data sets so that you can just use it for everything. Cool. So I won't go on anymore. We'll get to the next slide. Cool. Thank you.
Sorry to be late. So, my name is Gopal and I'm here to present Tygon to you. So, Tygon is a joint venture, joint project between CAST and HBase research labs. So, in one sentence, it's basically a real-time screening platform for the real world. So this is Tygon. Tygon is an open source distributed real-time stream processing framework. So it gives you exactly once processing guarantees. You can think about it similar to systems like Storm or Samsung, but it gives you exactly once processing guarantees. And also, it provides a Java API and also a SQL like this declarative language for building really powerful apps. And as John mentioned earlier, it's built on top of Loop, Yarn, and Apache HBase. And also, to repeat what John said, basically it leverages Tool, which is our Apache incubator project, and also CAST's open source transaction engine, which provides transactions on top of HBase, which is called Tetra. So in one slide, this is how the Tygon stack looks like. So we have Yarn and SGFS on the bottom. And Twill, as we talked about earlier, makes it very easy to write Yarn applications. And we have HBase on top of HBase. And Tetra, which is a transaction engine, gives you transactions over HBase, and it is implemented as a Yarn container through Twill. And Tygon basically leverages all these functionalities to provide a fault-tolerant, reliable stream processing framework. So on the right-hand side, you'll actually see a description of Tygon's architecture. So the Tygon architecture is basically a stream processing application. It's called flow, and you have multiple different flows. It's very similar to any of the stream processing framework where you have a directed acyclic graph. And these are represented by processing nodes, which are called flowlets. And the stream events come into these flowlets, and they do their processing, and then they pass it on to the subsequent flowlets. Now, you can have multiple flowlets. These are Yarn containers. You can have multiple of them depending upon your application needs. And the data, the communication of the events of data between the two flowlets is implemented in HBase through queues. So the nice thing about what John said earlier, you can run this entire application on what you call flow in either standalone mode or a distributed mode. A standalone mode on your laptop, a distributed mode in your Hadoop cluster. In standalone mode, all the processing nodes are implemented as threads, and the queues that you mentioned about, they're implemented in memory. While in distributed mode, the processing nodes are Yarn containers, and the processing nodes are Yarn containers, and the queues are implemented in HBase. So you can process these events coming through, and then you can finally persist it in HBase. And all the communication is all wrapped in transactions so that it provides you exactly one's processing guarantees. So you don't have to worry about at least one or most ones or any of those parameters. So for a quick demo, so this is what I have for a sample case. So you have two event streams coming in. And also I should mention about the special flow called Tigon SQL. So Tigon SQL is a library that we built for Tigon itself. And it actually contains AT&T's stream processing engine, so which allows users to do a lot of joins or filtering of streams that are coming in, and you can do that using SQL-like statements. So for example, there are two events. For example, I have two of these events coming in. One has an ID and name, and another event has ID and age. I can do a join between these two streams, and I can filter the data. And all this processing is happening in memory in that particular processing engine or flow bit. And this is implemented using the stream processing engine streaming database of AT&T. And so this, what it allows you to do is ingest a lot of data, do all the pre-processing in memory, so that finally when the resulting data actually hits HBase, you have very little amount of data, you have already done a lot of processing or filtering or aggregation that you want to do. And all the heavy lifting is done so that you can ingest a lot of data and you don't have to persist it in HBase directly, but only the results of these processing are persisted in HBase, so you get much higher performance and much higher throughput. And subsequently, these data from these queues are read by flowlets or yarn containers, which does the processing, and then finally it persists into an HBase table. So for a quick demo, so as I mentioned, that the flows or the applications are really yarn applications. So as you can see, I have multiple flows that are running. These are basically yarn applications. So what this gives you is a huge elastic scalability for your system. So as I mentioned, those flowlets, those processing nodes can be scaled up dynamically while your system is running, so that it can be reconfigured during. You don't have to stop your topology or restart again. It can be done dynamically. Depending upon your application, and change it up depending upon your application needs. And for a quick demo here, so as I mentioned, this is a basic command line interface for interacting with Tigon and the distributed one. So as I showed earlier, there's a one SQL input flowlet that's running its yarn container. Then there are three flowlets that are processing the output of the SQL flowlets, and then there's a transaction manager. Now I'll go ahead and show you that there's just no. So I'm just writing the final. So as you saw, there's a join of two events, and I'm finally storing the name and the count in HBase. So this table is currently empty right now. I'll go ahead and ingest a bunch of data. So these are two different stream events that are coming, two different streams. One with ID and name, another with ID and age. So those two streams are being joined. So those streams joining of the streams, and then they're being filtered as well using a SQL query. And that result is stored in queues, and those are taken up and processed by the further processing elements and flowlets, and then they're finally written to HBase. So as you can see, this data has been like combined, joined, and then written to HBase. So this is a very sharp demo, and so this is what the demo is in tutorial. And so we have announced the developer preview release. It's available for download from Tigon.io, and the source code is available on GitHub. You are welcome to download, develop, launch, fork, and contribute to the project. Yeah.
So when you do the writes, when you're joining the two streams, first question is, what is the source of the events? We have a flow event.
So you could write something like that, but off the shelf, like what you provide, or REST HTTP endpoints or TCP endpoints for you. and then you can get that endpoint to your device in JSON format or whatever format you want to ingest data. Because the reason why we wanted to provide this like a TCP interface so that we can ingest a lot of data. It's primarily focused on high throughput.
Underlying everything is TCP eventually. What I'm trying to say is, I'm taking a real production use case, trying to see if it really fits that paradigm. Okay? My question is, I have farms of my web service, okay, and we are doing a lot of TPS, which we want to ingest into HDFS. The question to you is, can these events are they source specific, or could it be, as long as it has your Taiwan interface, it could be any event?
It could be any event. So you do not use the SQL code and imagery, it's just a one action library that we provide. But those are generic processing elements, so you can pull data, you can have a Kafka line that's like using data, a Kafka subscriber, or you can write anything that you really want to get your data events from, and then further processing.
You can actually deploy code. How you can get it if there is a memory.
And one last question, thank you very much. When you write into HBase, right, how do you make sure that we have service bodies on the happen? Because usually, the way you design the scheme, basically, my trying to do some kind of intelligent row key distribution and maintaining hard identity and all that. So, do you need to worry about that, or once you're writing it, your thing is optimized to distribute it across the cluster, so you don't see any hotspotting or names.
So how the data sets right? So data set doesn't have any, it's not a code layer, it's not an intelligence layer, right? And so if I implement a time series data set as a data set, and I'm reading it right from time to data, the design of that data set, that's what determines whether it's going to be. And so part of the point of CF is to codify good implementation and make it very easy to surface the metrics.
Alright. So I'm going to be talking about Cooper, and I'll just describe what it is, very briefly how it works, and how we use it here at Castle across all of our development areas. So what is Cooper? Traditionally, Cooper is a task barrel maker. So for us, it's a cluster maker. What it allows you to do is it allows you to create a cluster with just a click of the mouse. So this is a screenshot I've taken from our Cooper UI. Pretty much all you do is you select some template, some administrator setup, give it a number of machines, click create, and then it goes on. Vision, so it's installed at the to install figures. And Cooper itself is actually doesn't know anything about Duke, just know anything about HBase. Everything, including the service dependencies, everything set up by administrator through these templates. And basically, what the templates do is give it a set of rules, and then Cooper will go figure out, based on these rules, what should my cluster look like, and what version of our function. So let's start quickly. So this is a cluster. It's a simple demo cluster I created a few hours before this event. So down here, we can go and what I have on this cluster is just HDFS and Smart. And what we're going to do is we're going to add HBase to this cluster. So you can see there's nothing running here. And what we're going to do is we're going to add our HBase master group. And region server. So to go. And at this point, it's figured out where it should add these services based on the rules of the template. And it's going to go and go to the nodes and install software figures are in the order that it needs to be. So very quickly, we're going to look at the template that this is using to see how that's done from an administrative perspective. So here you can see the constraints. So what we have in this template is we have things like the region server can always be on the same node as the node here, node manager. And out here we have something like HBase master, which is the same node as your main node. So just dividing up into master and server. And down here we're saying the master shouldn't be on the same node as the root server. And down here we have should have exactly one HBase master. And so what Cooper does, he takes all these constraints and figures out exactly what services should go on what nodes. And in another section, we kind of define different service dependencies. So like the root server depends on the rest. And based on that, you'll figure out what to do. So, well, let's go ahead and slide. We can talk about a little bit about how it works. So we have this UI, and underneath the UI is a set of REST APIs implemented by the server. The server is really responsible for storing all your cluster data, all your templates, all your services, and it's also responsible for solving what your cluster should look like, as well as planning out the tasks that need to be done and coordinating with the provisioners that here what to do. The provisioners are the actual workers that go through the tasks, so they'll like come to Google Compute, Amazon, whatever, to spin up your nodes. Internally, we use Chef to install software and configure it. This is pluggable, so if you're using Puppet or some other system to plug that in and install it, how should I install service? Start it. Yeah, that's a very high level how it works. And so now we go back and check files. It's the operation's completed. We go here. And HBase right. So how we use it internally is we work extensively on top of HBase and all the other technologies in the ecosystem. And so in order to be efficient and productive, it's very important for our developers to be able to have their own clusters and be able to test against different configurations, different versions of software. So for example, we have a template for spinning up a secure Hadoop cluster, Kerberos, everything is enabled and set up for you. So me as a developer, I have to understand how to set that up. It makes my life a lot easier. I can just worry about development. Similarly, like I don't know how to install Hive, but our template does that. So I can just spin the cluster up half an hour later and something running. I can use so that's kind of how we use it internally. Each developer has their own cluster. And similar, since it's backed by the REST APIs, you can do things like you want to run integrations. Our platform has to work with different versions, different distributions, on different OSs, security or not security, all these different combinations. And we couldn't just automate that all. Just do REST calls to create a cluster, deploy things. All that can be automated. So it really has made us a lot more productive in both developing and testing. So that's just kind of question.
So how does this compare to something like Letterman or Ari for cluster management?
Yeah, so the biggest difference, so for a lot of those things, it doesn't handle, let's say, the creation machines. Right? So we have different plugins that will talk to AWS, Google, whatever you want to version. So it's a full end-to-end. Right? So the other thing is that it's completely agnostic to the services and the software that you're running. So it doesn't know anything about Hadoop, it doesn't know anything about HBase. So if I wanted to, say, add another set of machines to my cluster setup, and have Apache and I'm hosting some service that reads from here, whatever I want to do, I can add it to my template. So it's more flexible and yeah, so the question was about Chef books that we use for open source. So yeah, for open source, so we have like a new cookbook, we have Rapid for to today open source our CDAP notebook.
You maintain the shepherd. The shepherd.
The DevOps team at Task actually is the maintainers of the ops code. And that's what it is.
When you have a cluster, a HBase cluster, so the templates, either predefined templates or we define them, or we.
So the question's about templates, whether it's predefined or defined. So we include some of the templates that we use, like Hadoop, the LAMP, MongoDB, CDAP. It's kind of references for what you do. And beyond that, the system has Notion as some administrator. And the admins are saying like the DevOps team does this, so they can add whatever tools or services they want. And then we provide this kind of base template. So,
They have the API.
yeah, API interface to
It's available for you right now. Right.
yeah. We're done by so one more.
So if you want to set up a cluster on AWS, what kind of information do you provide? Instance types, the other activity, the amount of disk space and so on, all of that is what we have here.
Yeah, so let me show you. So this is our plugin for AWS, missing some of the things. I should show you. But so it has a notion of different keys you can upload as well as the fuller version has different how much disk you want to use, whether it's easy or not, a whole range of like 20 different settings included in the plugin. But these pieces that talk to AWS or Google or whatever are also pluggable. So if you want to use something like internal system or if you want to add another one.
So as part of your stack, is there any monitoring thing that, let's say we provision a company to
So there's not like full on like Agios or anything like that. And the system doesn't keep track of whether your services are running or not. Just simply that starts off those things are happening. So adding something like that is on the roadmap. But internally, what we do for monitoring is we set up a service for ourselves that will get installed on each node. And so we've kind of abstracted that piece away from the system for ourselves currently. But it's on the roadmap. Yeah, exactly. Yeah, so the server is just a Java server running, and it exposes a bunch of REST APIs that are on it. So you can write a script. So we have ourselves a script that will talk to the server and create clusters with special flags for configuration and instances. And that's also how you use it for like integration test operation. Well, I think there are no other questions. Thanks very much.